Hello everyone, I am Dr. M. Manikam, Assistant Professor, Department of Physics, Dr. SNS Rajalakshmi College of Arts and Science, Coimbatore. So today in this video, we will discuss about tunnel diode. So actually this is a lecture series video. So continuously we are talking about basic electronics and microprocessor, things like that we are continuously discussing. So today we will detail discuss about tunnel diode. So in this video, what is tunnel diode, what is the working principle of tunnel diode, and characteristics and applications. So these are all the things we'll discuss. So let's start. First of all, what is tunnel diode? So a tunnel diode is a very heavily doped p-n junction diode. So in a tunnel diode, electric current decreases as the applied voltage increases. So and at the high voltage it works as an ordinary p-n junction diode. So when compared to ordinary conventional p-n junction diode, so it is a heavily doped p-n junction diode. So when it is the voltage increases at the high voltage, so it works ordinary p-n junction. In tunnel diodes, electric current is due to the tunneling effect. This is the tunnel diode. So how it is working principle and all we will discuss here. So this is the symbol of tunnel diode. So one end is anode terminal, another one is cathode terminal. So this is the symbol of tunnel diode. So the tunnel diode is invented by the Leo Iseki in the year 1957. So that's what this tunnel diode is also called as Iseki diode. So we can also called as Iseki diode. So a heavily doped p-n junction diode that exploits the quantum tunneling effect to enable ultra fast switching and negative resistance. This is the definition for the tunnel diode. So which was the Leo Eseki is recognized by the Nobel Prize in the year 1973 for physics. So first manufactured the company, that is Sony, in the year 1957, and then the alternate name I told you like that, Iseki diode. The anatomy and component of this tunnel diode is so first picture shows the physical and symbolic representations of tunnel diode. So ordinary diode with some tunneling, anode and cathode terminals is there. So here p-type material and another end is n-type material. In between it is very heavily doped. So because of heavy doping, so the depletion layer width is very narrow, so or very small one. So this is the comparison for standard p-n junction diode and tunnel diode. So doping level, so is for standard p-n junction diode, so light to moderate. For tunnel diode it is extremely heavy. Then depletion width is wide in p-n junction. It is ultra narrow. Then current mechanism, so that for p-n junction over the barrier. Then quantum tunneling for tunneling diode. So VI behavior, VI characteristics, that is linear increase, negative resistance phase for tunneling diode. So primary utility for p-n junction is rectification purpose. Then tunnel diode is utilized by high frequency oscillators. So the quantum tunneling, how the working mechanism or working principle of the tunneling diode is a standard diode jumping over. So see the diagram. So the electrons or the charge carriers or holes or electrons require high potential energy to jump over the wide depletion barriers or break down wide. Need more energy to break down the barrier or jump over the potential barrier. For tunnel diode, so already we know that the potential barrier depletion layer is very thin, so it is easy to move from one end to another end by the electrons or charge carriers, so with a small amount of energy. So this is the tunnel diode. So first step, step by step explanation for the working principle of the tunnel diode. Unbiased state. So energy band, this is the energy band diagram. So n type conduction band and p type valence band is there. So energy is exchanged, I mean charge carriers are moving. Heavy doping causes the bands to natively overlap, so electrons tunnel equality is both directions. So this is the energy band diagram of tunnel diode. So then we characteristics curve, that is the in x-axis voltage and y-axis current. So V is equal to 0, the net current is exactly 0. So this is step 1, unbiased state. So net voltage and current is 0. Then peak alignment surge, that is step 2. This is the energy band diagram. Here tunneling current surges to its absolute physical maximum. So the peak point, that is Vp or Ip. So that is a peak point. So small forward current here we are applied, forward bias applied, then energy band is aligned perfectly, allowing maximum electrons to tunnel. So this is the explanation for peak alignment when applying the forward bias. So as the voltage increases beyond the Vp, I mean Vp voltage, then bands severely misalign, electrons lose empty states to tunnel into. So here the band energy band diagram shows the misalignment between the n type and p type when increasing the voltage beyond the Vp. Then see the diagram VI characteristics, that is it is defining the phenomena. As applied voltage increases, the current physically decreases. So once it reaches the peak point at a time, then it is suddenly it decreases to the valley point. Okay, so this region, the dotted line regions, is called the next negative resistance region, or we can call it is peak point to valley point. So here the negative resistance is the key point or key mechanism of tunneling diode. Then fourth step or next stage, that is saturation or normal operation. So here overlap is completely eliminated. Quantum tunneling drops to 0. High voltage pushes electrons over the barrier. So here again we need at the saturation mode we need more energy. So it will the electrons are pop into the p-type valence band from the n-type conduction band. So see the diagram for this saturation mode. So the third step from the valley point, so it is reaches the maximum, that is the saturation point. So it's in saturation point or saturation mode. So this diode is exactly working like a ordinary p-n junction diode. So this is the graphical representation of VI characteristics. Ohmic region from starting 0 to peak point, then from the peak point to valley point, so this is the negative resistance region. So this is the tunneling effect is happening here. Then after the valley points, it reaches the saturation region again if you are increasing the forward voltages. So engineering trade-offs, that is advantages and limitations of the tunnel diode is ultra high. Advantages are ultra high speed operation, then extremely low power consumption, then long operational lifespan with a very low noise, then compact physical footprint and inexpensive materials we are using in this tunnel diode. So the limitations are being a two terminal device. It provides no proper DC isolation between input and output. So this is one of the drawback. It operates within a very small voltage swing, so it cannot use for the large scale applications. So then its yield, so notoriously difficult to must fabricate the consistently at the score. So these are the some limitations of uh, tunnel diodes. Then the applications of real world applications of the tunnel diode, that is we are used in the microwave oscillators. In microwave oscillators we are using harnessing the negative resistance slope to generate high frequency wave oscillators. This is the purpose we are utilizing this tunnel diode in microwave oscillators. Next one, ultra fast switches, FM receivers. In FM receivers, it acts as a ultra low noise signal amplifiers in high frequency communication systems. This is the one of the application. Then relaxation oscillators. So these are the some applications of tunnel diode. A quantum phenomena successfully packaged into a practical component. So this is the key point of this tunnel diode. So thank you for watching this video. Thank you. So in our next video we'll continuously talking about the basic electronics and diodes and all. So thank you for watching this video.